So yeah, so as I mentioned, I will start with an overview about ALMA. But actually, before I really started to talk about ALMA, I'm going to give some advertisement about NRAO, which is the National Radio Astronomy Observatory. And I have to do this because, you know, they are paying for our coffees and lunches. Um, so as I mentioned, NRAO is National Radio Astronomy Observatory. And they have a headquarters located in Charlottesville, Virginia. So it's actually a building within the campus of University of Virginia. And they are funded by the National Science Foundation for doing radio astronomical research and operating radio telescopes. So as you might already know, NRAO operates ALMA, which is the image on the top over here. But also, in addition to ALMA, they operate many well-known telescopes like the Jansky Very Large Array, VLA, which is located in New Mexico. And it is actually operating in a longer wavelength than ALMA. So VLA and ALMA actually together like span a pretty wide range of frequency coverage in millimeter wavelengths. And also NRAO operates the Very Long Baseline Array, or VLBA. So in this image, you can see the red dots are showing the location of their antennas. So you can see it is very widely spread across the globe. So there are in total of 10 antennas, and the maximum baseline is from this here, which is in Hawaii to the Virgin Islands, and it spans about 8,000 kilometers in terms of baseline. So this is for getting high, like super high resolution data, and I will explain more in my interferometry talk. And so now we've covered VLA, VLBA, and ALMA. I want to mention that actually very recently, the Green Bank telescope has been reintegrated back into NRAO. So GBT was part of NRAO until 2016, but then they operate independently as the Green Bank Observatory. But I think actually starting October, so it's starting this month, that GBT is now back to NRAO. All right, so there are also some exciting ongoing projects that NRAO is working on, such as the next generation VLA. So the NGVLA will cover a wide frequency coverage from 1.2 gigahertz to 116 gigahertz. And you can see from this map, it shows the locations of their antennas planned. So in total, there will be like 150 antennas, and it consists of a core array, which already spanned across several states, from Arizona, New Mexico to Texas, and there are also some antennas in northern part of Mexico. And in addition to this core main array, they also have a long baseline array that also includes stations in Hawaii, California, Washington, Iowa, and West Virginia, and also the Virgin Islands. So this will form a longer baseline array to give us high resolution image. So if you're interested, there are many information on the NRAO website, and even more, you can be involved in their NGVLA science working groups to help them identify if there are any missing requirements for the development of NGVLA. So I want to briefly mention that you may have noticed that these radio telescopes are all on the ground, as I shown from the figure. So this is actually because we know these radio wavelengths have longer wavelengths where they can actually penetrate through the Earth's atmosphere. So this is not like shorter wavelengths like from UV, gamma ray, or X-ray. There we have to rely on space telescopes to observe. So especially I mentioned that with both VLA and ALMA together, they cover from centimeter, millimeter to radio in the spectrum. So there is a strong synergy between these NRAO telescopes. So just for example, in terms of studying the interstellar medium in galaxies, we know VLA is good at detecting atomic hydrogen, which is mostly in the outskirts of the galaxies. And ALMA is good at detecting the molecular gas, which we know is the ingredient to form stars, and it's in the inner disk of galaxies. So together, using VLA and ALMA, we can map the full gas distribution of galaxies and understand how these gas and star formation impact the evolution of galaxies. So there's actually a wide range of science we can do with NRAO telescopes. So as you can see, the topic can range from very local to distant universe, including our solar system, nearby star-forming regions, and all the way to like exoplanets and large-scale structures like galaxies, galaxy groups, clusters, and cosmology. So I guess the point here is just that whatever science you are working on, it is likely that ALMA or like NRAO telescope can always be helpful in some way. So, okay, that's the end of advertisement for NRAO. So let's get into our focus today, ALMA. So ALMA consists of 66 antenna, and it is located at 5,000-meter elevation in the Chilean Andes. So the whole ALMA project is actually a collaboration between Chile, North America, Europe, and East Asia. So the headquarters in North America is, of course, in Charlottesville, as I mentioned, the headquarters of NRAO. And for Europe, the science center is at ESO, the European Southern Observatory in Garching, Germany. And in East Asia, the center is located in NAOJ in Japan, but it is also cooperated by Asia A in Taiwan and PASI in South Korea. So I do see some online participants from countries outside North America. So if you need any help or have any questions related to ALMA, you can definitely contact the Science Center that is nearest to your location. So as I mentioned, so ALMA consists of 66 reconfigurable and high precision antennas, which actually includes a main array with 50 12-meter size antennas. And they also have a more compact array consists of 12 7-meter antennas. And also there are 4 additional 12-meter antennas using as total power, which is the single dish observations. So I will talk more in detail later about like why we need all these different configurations. So in total, there are 192 possible antenna locations, which means we have array configuration spanning from 150 meter to 16.2 kilometer. So by array configuration, I mean that the maximum baseline for a configuration can range from 150 meter to 16.2 kilometer. So this huge dynamic range of baseline is exactly why ALMA is so powerful. So as an overview, ALMA is currently the state of the art, and this is not only because they have amazing sensitivity due to the huge collecting area formed by huge number of antennas, and also because of their huge number of baselines, it really provides excellent image fidelity. And another great thing about ALMA is it has a wide spectral coverage. So the figure you see here is showing the atmospheric transmission rate versus the frequency. So the vertical shaded area are the bands ALMA cover. So it's band 3 to band 10 over here. And you can see that each window have at least a 50% transmission rate. So ALMA basically tries to cover as much band as possible in the millimeter wavelengths. So as a summary, ALMA can reach super high resolution down to like 0.005 arcsecond. This is measured in the highest frequency band at the most extended C10 configuration. And it also has amazing sensitivity that can be 10 to 30 times better than other current millimeter interferometers. So I'll just go through this a bit. Like ALMA is state-of-the-art in terms of low noise, wideband receivers, and they have high spectral resolution at wide bandwidth. They also have full polarization capabilities. And actually, I think one of the best part about ALMA is that it really provides great support on the science and data processing. So they create many useful tools that make it really easy to propose for ALMA observations and to reduce and process the data to make them science ready very quickly. So currently, ALMA has been giving us great science for over a decade, and the routine science observing has been out to the most extended C2 baseline, which means it's greater than 16 kilometers. And I want to mention that for every PI science project, ALMA actually guarantees you with a minimum of 43 antennas in the 12-meter array. And for ACA 7-meter observation, they guarantee a minimum of 10 antennas. So this is because several of the antennas will be undergoing maintenance and they take turns doing that. So an exciting thing starting this cycle is actually that now 9 of the 10 bands are offered from C1 to C10 configurations. So that means like all the bands and all configurations are possible, except for the band 2, which they are still under construction. Okay, so you can always find the latest information about ALMA on their science portal. Just type in almascience.nrao.edu. So this is an easy website, including all the documentation information that ALMA needs. And also NRAO holds many ALMA-related workshops, just like this one. But like this one is the data processing workshop, and they actually also have proposal preparation workshop every year before the ALMA proposal deadline. All right, and another ALMA website other than the science portal is the observatory website. So here, this is targeting for a more broader audience, including scientists and general public. So here you can also find many information like outreach events and definitely a lot of pretty pictures and their science highlights. So in the last few slides, I just want to bring up some key science highlights from ALMA. So I'm sure many of you already know one important breakthrough with ALMA is on the protoplanetary disks. So in case you don't know what protoplanetary disk is, it's a disk of gas and dust surrounding a young star, and they will provide direct information to help us understand how planets are formed on those disks. So as you can see here, so here, all 6 figures here are showing protoplanetary systems, but these are observed before ALMA. So you can see, although we can detect the disk structure, but there's nothing really resolved within the disk. And now I'm going to show what ALMA observes. So you can see there's a very big difference on how ALMA really resolved the detailed disk substructure. So just to give you a sense of how high resolution this is. So for example, this TW high-res system, the angular resolution on this image is only 1 AU. So that's the Earth-Sun distance. And just to mention that TW Hydra is also the data set we will be playing with in the afternoon for imaging and calibration. Okay, and another science topic that ALMA is great for is to study the star formation in our local universe. So this is because ALMA is good at detecting molecular gas using, for example, the carbon monoxide, which is the most widely used tracer for molecular gas. So here you can see some images from the FANGS ALMA survey, which they map CO2 to 1 transition at 100 parsec scale for almost 100 nearby galaxies. So this really reveals detailed structure of molecular gas at giant molecular cloud scale. So here you can see they actually cover a wide range of galaxy morphologies, including those with bar, without bar, with like grand design spiral arms or some flocculent galaxies. And here is a compilation of all 90 galaxies from FANGS. So you can imagine like these large sample of galaxies at giant molecular cloud scales has really allowed us to systematically study how star formation at small scales are connected to the large scale galaxy environment that drives galaxy evolution. So as a member of FANGS myself, of course, I'm going to sneak in some of my own work. So just want to mention ALMA is useful not only in detecting the typical carbon monoxide. By typical, I mean 12C16O. So ALMA is also sensitive enough to detect much fainter CO isotope log lines, such as here you can see 13C16O detection and 12C18O detection. So here you are seeing images of the center of M100. So you can see like in both the typical carbon monoxide and like CO isotope logs, like they are all well detected in even in this very central compact nuclear region of this galaxy. And you can definitely see like some like even more compact nuclears and like some gas inflows getting into this very central region of galaxies. Okay, so finally, I also want to mention that even in the distant universe, ALMA has also opened a new era of cosmological surveys. So for example, here I'm showing the ASPECTS program. So this is the first line deep field. So this means that they are actually targeting the Hubble ultra deep field, and they have detected CO emission from various galaxies at redshift 1 to 5, and they also detect some ionized carbon emission for even higher redshifts. So you can imagine these data have been very useful in constraining the dense gas history and the star formation history across the universe from low to high redshifts. Okay, so at the end, I just want to let everyone know that there are many supports from NASC, the North America ALMA Science Center at NRAO. So the most important one I would say is the ALMA Help Desk. So this means if you have any questions or need any help related to ALMA, just submit a ticket to ALMA Help Desk and they will respond to you within 2 days. And they also offer a wide range of financial support, such as the student observing support. Yeah, so if you have ALMA data or you have any idea using how to use the ALMA archival data, you can apply for this student observing support. And they also provide support for organizing workshops or conference related to ALMA. And also if you publish any articles with using ALMA data, they will support you for the page charge. So I think the page charge, they actually determine the percentage of support by the percentage of authors in the US institutions. So also, NASC really encourage people to apply for their face-to-face visitor program. So if you need to discuss ALMA proposals or you're not sure how to reduce or process your ALMA data, you can apply for a 1-week visit in Charlottesville, NRAO Charlottesville, and they will cover all the travel expenses. And they also provide support on computing cluster. So if you have data, but you don't have the resources for data processing, you can also apply to use the computing cluster. And there are also education and training events, just like these workshops, and they also provide quite a few videos introducing basic radio interferometry on their website. And finally, of course, the ALMA Ambassador Program, which is the reason why I'm here. So you can also become an ALMA Ambassador if you are based in North America Institute. So personally, I think this is a very good program because not only they provide you training with organizing proposal and data processing workshop, but they also provide you a 10K research funding support, which is amazing and very generous, I think. So yeah, so just apply if you're interested, and you won't lose anything to apply. Right? Okay, so this is my talk for ALMA overview. So before I move on to interferometry, are there any questions?